Hi, I'm Josh Lovell, Product Line Manager for Teledyne LABS Pharmaceutical R&D Products. Thanks for joining our regular chromatography webinar series. Today's topic is focused on how you can use stacked injections in your chiral and achiral purifications as part of a new peak track software feature on the ACCQPrep HP150 Preparative HPLC. As a reminder, if you have any audio-video issues, please exit the webinar and rejoin. This usually resolves the issue. If you have any questions during the webinar, please type them into the questions box. Some questions will be answered at the end of the webinar, while others will be followed up with after the webinar. The webinar will be recorded and made available for future viewings. The title for our webinar today is 3 Quick Steps to Stacked Injections, a hat trick for large-scale chiral and achiral separations. We're excited to introduce one of our Teledyne LABS global chromatography application specialists, Todd Anderson. Todd is one of several application experts that we have at Teledyne LABS to help with customers determine the best route to a successful separation. Prior to joining Teledyne, Todd performed many chiral purifications on HPLC and SFC using stacked injection processes on a regular basis. For any of your tough separation questions, please reach out to any of our experts with your questions. At this point, it's my pleasure to hand it over to Todd.
And thank you for joining us today for our webinar, 3 Quick Steps to Stacked Injections. We've labeled it a hat trick for large-scale chiral and achiral separations. Personally, because I'm a big hockey fan and we're in the middle of the NHL playoffs, so I thought I'd go ahead and do something fun with a hat trick. Today's goal is to actually be able to help you better purify samples in your lab by using the stacking functionality of both the ACCQPrep and the ACCQPrep SFC instrumentation. So hopefully you get something out of this today, and if you have any questions with what we present today, by all means reach out to us and we can follow up later, or Sharon will, or you can reach me directly through my LinkedIn at the end of the webinar. So let's get started. Today's prep topics are going to be basically on the chromatography types, column options. We're going to skip over the particular mobile phase additives and stuff like that. We've done some other stuff on previous webinars that if you reach out to us, we can bring them up to your attention. We'll be optimizing the gradients a little bit, and then we'll get into the stacking and optimizations for both mobile phase and detection. So today we're basically going to be focusing mainly on the chiral and achiral options that we have added to our ACCQPrep software, but we'll go over different types of stacking throughout as well. But as I said, we're going to try and stick with the chiral and achiral options right now. So with chromatography, there's so many different types of chromatography, everything from gas to liquid. We have SFC, which is sort of a hybrid. What we're going to try and do today, though, is focus mainly on SFC for a little bit, just to get you started with what stacked injections are. And then we're going to stick mostly with the liquid chromatography after that. So with the focuses that we're going to be looking at today, we're going to start a little bit with normal phase and reverse phase prep chromatography, blending in a little bit of the chiral chromatography into both of those, as well as into the SFC chromatography, which is both chiral and achiral, as I mentioned before. So here we go. Now we're going to step into some of the column options that we have for doing some of this chromatography, whether it be reverse phase, normal phase, or SFC. Depending upon what type of separations you're going to do. So some of our instruments, we have, for instance, the normal phase HPLC systems, which typically will do more normal phase type columns, silicas and stuff. We have SFC, we have reverse phase, which are going to be water-based with acetonitrile or methanol. And then there's also SFC, which is going to be mostly CO2 and methanol, but sometimes some other solvents will get used in there as well. And here's the representation of the different columns that you might be looking at either the normal phase or reverse phase. So I had mentioned the normal phase would probably be a normal phase column, so maybe a silica, alumina, And that's usually what we mostly see, but you can do some chiral with normal phase solvents. The other thing we would look at is reverse phase. So that's going to be more of a C18, maybe down to a C4 and some other interesting columns, but also as well the chiral columns. And interestingly enough, SFC actually can use both types of columns. May not work as great with certain solvent conditions, but at least it'll cross over to both normal and reverse phase into the SFC route. So these are traditional chiral columns that you would see with the chiral technologies stationary phases. Other companies have actually mimicked a lot of these as well, but what you're seeing on this particular slide is there's immobilized on the left-hand side and coded on the right-hand side. Typically, the coded stationary phases are going to be more normal phase using hexanes and some form of alcohols. The immobilized columns, however, opened up a much broader use because we have an immobilized stationary phase that we can actually use things like water and acetonitrile or water and other types of solvents that will give us better solubility and a little bit better ability to do various things with the columns. They're a little bit more robust too. So this is typically what they would do, chiral technologies, to determine what kind of column and separation you need. This is just something that I put in here so that you could actually go back to it and reference as far as what's the best type of separation. And so from here, you can sort of get an idea of whether or not you need to go more IPA, ethanol, and then as you can see on the right-hand side, there's some of the immobilized phases where they're using DCM and MTBE and ethanol. Now with SFC columns, it depends on what you're going to be doing. You can do achiral or chiral separations. Typically, the chiral columns are going to be similar columns that you would do for normal phase or even some of the reverse phase now, chiral stationary phases on the other instruments. But with the achiral columns, you're going to typically be looking at something totally different than what we typically see on reverse phase. Would almost act more like a normal phase separation on the SFC. As far as mobile phase optimization, I'm going to leave that to some of the webinars that we've done in the past. We have several of them out there that if you go ahead and reach out to us, we can certainly point you in the right direction to grab those off the internet, or we can even send you copies of them. Gradient optimization I am going to get into a little bit because there's been some changes to the ways that we now do some of our gradient optimization, and it will help us with doing our stacking protocols. So scale-up has typically been done from analytical to preparative purifications pretty straightforward in the past. Most people will take multiple zones based on the elution on the analytical column, and they'll do an extrapolation to what that optimal gradient would be on a preparative column. So in this particular case, I'm looking at this peak at maybe 5 minutes. So if we took that peak at 5 minutes on an analytical run and tried to purify it, we would typically run a 25 to 45% gradient as seen here on zone 3. Now, what happens if we get a peak closer up here to 6 minutes, that's almost between zone 3 and 4, or something back here around 4.1 minutes or even 4 minutes itself, that's sort of between zones 2 or 3. You might actually get that compound come off either before or after the middle of your purification. So we want to try and prevent that. And in order to do that, what we've done is actually incorporated some algorithms so that we can do one simple run, take that time point, and then translate it into the optimal gradient profile to run that sample. How do we do that? We do that with our peak track focus gradient generator. What we do is, you can see, I mentioned before about having a chromatogram where you run 5 to 100%, or even maybe 10. But basically we get your purification looking nice as a general guide, but suppose we want to get these two peaks separated a little bit further if we want to load up and scale up more. We would typically click the button right there that says focus, and then this window would open up. And from there, we can choose any time point on this specific chromatogram to go ahead and isolate that specific retention time. So if you do have a pair of enantiomers or isomers or something that you need to get a much better resolution, we can certainly do that just by using this. From here, we can also choose multiple columns to go into, assuming that you're using the same mobile phase and the same column type to make sure that that generates the same separation. This slide is a real-life example where we took this one main peak here at about 5.5 minutes. I was told it was pretty much pure by the analytical department from the customer that wanted us to test this. So we separated, and I was thinking I was trying to separate out some of these other components that were up in the front. Turns out he was trying to separate this out. Later, after we got the purification completely finished, he mentioned to me that they in fact did see a 30% impurity when they were running it on NMR. So with that, we were able to actually prove that there was an impurity there, and not only just prove that it was there, but we were able to get about a 99% yield or purity and high yield about 99% as well. So this is how it can actually help you in a real life scenario. Next, we're going to step into the new feature that I had mentioned earlier, and that is our isocratic prediction. So with that, we're going to use the PeakTrack software to not just generate a shallow gradient, but we're going to actually try and find the isocratic elution, as you can see here. So we took this peak and we did the same exact process, and we're able to get an isocratic run. But it allows for us to do a lot more with stacking and some other applications, maybe even some chiral applications. And the nice thing about the software is it is backwards compatible with all of our older systems. Now that we've gotten ourselves a isocratic method, which is critical to doing stacked injections, we're going to go ahead now and actually get into what stacked injections are and how they can benefit you. What exactly are stacked injections and what are the requirements for them? As I mentioned before, isocratic elution is the imperative for stacked injections. We will be having a repetitive sample injection throughout the process, which you can see here by these dashed marks. The fractions can be collected into a single vessel, onto multiple vessels. We can reuse tubes over. If the tubes fill up, as you can see right here, we go 5, 6, and then 7, 8, 9, 10. So we were basically using all different tubes. If we were going back and forth to 5, 6, 5, 6, we can actually do what we call fraction pulling, and it'll allow us to minimize the number of vessels that we use for collection. And it's going to optimize the amount of compound we actually purify at any given time. So what does that mean? We can do a comparison quick to see the differences between a traditional run and a stacked injection. So if you do 7 injections, about 3 minutes per run, we're going to look at about a 21-minute run. With that, we're going to only be able to purify 7 injections in 21 minutes. With the stacked injections, we can actually take that and use the cycle time and actually create 7 injections on column at the same time, repetitively. So we can actually do all of that stacking and purify the same exact amount of material in about 9.9 minutes. So we'll basically take less than half the time to get the instrument back up and ready to go for the next sample. What does that mean? Well, it doubles your throughput, but this can also be greatly utilized for samples that are longer eluting, have a larger cycle time, a longer runtime, and we'll get into those values here in a second. Begin with stacked injections. The first thing you're going to need is a relatively clean sample so that you aren't taking and reintroducing your impurities on top of the other compounds that you want to cycle. So it can be separated with an isocratic elution only, and you should probably have almost full resolution. So traditionally, runtime is the whole entire run from 0 till after your peaks are off. So in this particular case, we're looking at like a 2.75 minute run. The other thing we need to look at is cycle time. So the cycle time, this is going to be the time that we basically are going to keep re-injecting that amount of material, that time point throughout the entire run. Or we can let the software do that for you. And I'm going to show you that on the next slide. With stacked injections, what we can do is it's pretty simple to go ahead, once you have an isocratic run, and this is using our SFC instrumentation. We have other webinars that go through this that you can pull up, and we'll go into more detail. But basically, we'll just stack injections, click on the button, and that brings up our stacking optimizer. So if you look at this, right now we're only looking at one actual injection, a real-time injection. And we can see the two main peaks and then the impurity. But what the software does, it will take that window and cycle it based on the cycle time up here, and it will put them in sequence so that we can actually see what the stacking process would look like if we were to actually run 3 injections. We can do it just for the single injection. We can actually make those disappear by clicking on a box. We can also come in here, and in this area we would change our cycle time. Like I mentioned, that gives us that little gap right here between the second peak of the first injection and the first peak of the second injection. So if we need more room, that'll separate that out. We can also adjust the total sample that we want to put in here. So in this particular instance, we can put in how many injections, the total sample, and it will allow us to basically extend this run for as long as we want to and manipulate the amount of material we want to put on the column with each individual injection. The other thing we will look at is the time windows that we have here for these peaks. So in this particular instance, in the past, it's been very common for people to use that middle window as an additional fraction, that anything that sort of overflows into that area, they'll go ahead and take that sample to use to make up and rework their sample later. Then the two main windows are these two, and you can actually have them as being peak or collect all, and we can change the time windows right here, as you can see. So we can make this a little bit wider or a little bit smaller depending upon how much material we actually have on the individual injections. And that brings us to the topic for today's presentation. Stacking purifications on the ACCQPrep HP150, a hat trick for large-scale chiral and achiral separations. So I guess I should get into why we called it 3 quick steps. So if we want to take a look at the peak track focus generator again, as we had mentioned before, we were able to generate an isocratic elution profile from a run based on a typical gradient run. It's a new functionality to our software, so it's pretty easy to pick up, but if you haven't used it, it would take a new software update to your instrumentation. All the new instruments are actually shipping with it. And with that, we can have a one-click predictor for an isocratic sample. For step 1, we're going to actually run a representative sample and get a basic chromatogram so that we can actually go ahead and run on to our method development. And what we're going to do is, after the run is over, we're going to choose this focus gradient button, which allows us to bring up this window right here. Once that window comes up, there's going to be this 0% isocratic that I've chosen up here. So this is just basically a zoomed in version of that little area so you can see it. So as you can see, we can do 0, 5, 10, or 20, and that's a plus or minus. From there, we can choose isocratic in this particular case. And I'm going to go ahead and choose a time point somewhere on the chromatogram to go ahead and bring that retention time over into an extrapolated run that we can put onto this column right here. For step 2, we're going to optimize the conditions for our separation. We can use a post-separation pause on the injection process when we actually put in our sample information. And that allows us to pause the instrument between injections so that we can actually optimize, change the methods. We can also bring in our remove and add references so we can compare previous injections to help us find the best reproducible purification with the best isolation of our compounds. Continuing with step 2, we're going to go ahead and do this modify view. And under that, we can actually add and remove traces. So the first injection we made was really, really long, almost about 7 minutes long. Now we ran one at 50%, and I was able to get this type of separation. We went from the 42% down to 50%, sorry. And that brought our peaks in considerably. So now we are more like 3 and 5.5 minutes. I still think I would want to optimize that a little bit more, however. So what we'll do is we will remove that trace and add the 50% back in. And I wound up settling on a 58% condition. So with that 58% condition, I was able to get peaks somewhere around 2.5 minutes and 4 minutes, which allows us for the best, one of the best cycle times that I was able to come up with. Then we click on the Stack Injections button right here. So that allows us to go ahead and choose all of the same exact conditions and parameters that we're used to using in our SFC instrumentation as well. So the first thing we're going to do is we're going to look at our cycle time and make sure that the times between these two peaks, so this is our peak 1 and peak 2, and we are simulating 3 injections. So this is actually the first peak of the second injection and the second peak of the second injection. We want to make sure that we don't overlap these. So that's where we're going to change that cycle time. That cycle time will bring this peak a little bit further back if we extend it. We can actually put in how much material we want to process. So we can actually load, in this particular instance, it's 0.9 mils of sample at 0.3 mil injections. I can increase that with the post-separation pause as well. So we can optimize that timing also. The next thing we're going to do is we're going to optimize the windows for our individual peaks. So with this, we can either do all or we can collect peaks. It's up to you. My preference is I usually collect all, and then I just basically optimize my windows according to that. And in this case, we can make these windows wider or narrower. Another option some people will do is if you have a very tight separation, they will put a third window right between these two peaks so that you can get any mixed fractions for future reference. Then we're also going to make sure that we have our fraction pooling, which allows us to go from tube 1 to tube 2, back to tube 1, and then back to tube 2. And you'll see some of that as I go ahead and start processing some of my sample. Next slide. 3 is we're going to process. So in this particular instance, the software automatically tracks the volume of each individual tube. So you don't have to worry about overfilling the individual tubes. So as you can see here, we started out in tube 3, tube 4, and then we filled up tube 3, so it moved on to tube 5, and then it continued in that pair as 5 and 6, and eventually we went to and filled up tube 8, so we wound up going to 6, 7, and 7, 8. We have great reproducibility with our injections. And in order to demonstrate that, I basically made 3 separate injections. And then on a fourth, I basically did a 50% more injection. And you can see that we actually did get a much larger response out of that fourth injection. The nice thing about this is these are only 18 by 150 millimeter tubes. And that's why we're transitioning to the tubes much quicker than I would normally do it. We can also do 25 millimeter tubes, and we can also do the square French bottles as well to help you reduce the amount of wasted tubes. And the nice thing about this is it's not just for chiral purifications. In this particular instance, I went back and went directly into a single component, which was supposed to be a single component, but we knew there were some other impurities based from other chromatography that we had been doing. So as you can see on this chromatogram, we actually have 3 different impurities that we're looking at. The other compounds, this right here and this right here, were residual left in the instrument due to the sample that I had previously been running on the stacked injections right prior to this. So we're going to go ahead and purify this, and I'm going to show you how this can be a little bit different than the injection we just did last time. In this particular instance, we got one peak, which actually does have a slight impurity on the tail edge. It's hard to see on the red trace, but on the purple, pinkish trace, you can actually see it on the back end that there's a little bit of an impurity there. We'll also notice that there's this really, really late impurity that required us to go to a 100% kickoff. So I'm not going to really worry too much about that impurity, but there is this one up here that I don't want to get this small impurity to co-elute with this purity here. And the issue with this is we have a compound that we need to get to basically 99.999 purity. So any impurities in there could actually cause a lot of problems for down processing. So that's why we didn't want to have any of this compound at all co-eluting with this. But now that we can see both impurities and do the predictor. So we've just basically set up an isocratic run and we set up our stacking. We know that we don't have to worry about the late impurity at all because that's going to require a high kickoff with 100% organic. We can isolate that little back window, and if you want to shave off a little bit more, you could. But basically, I put my retention times such that, or the peak window times such that we can just take that little portion off and collect the bulk of the rest of the material. As you can see here, it's simulating 3 injections, like I said. This is the first early eluting impurity. And you'll notice that we have 3 of those. And I want to try and optimize for a 4th. And I think we have the 4th would wind up coming out pretty close to the beginning of this main first peak. But when we go ahead and run, you'll see that it actually worked out quite nicely. What I was able to do is actually stack this, and we removed the 4th peak right here. We held off on the peak a little bit, but we got 1, 2, 3. The 4th impurity is actually up a little bit. So we got all 4 impurities out before our main peaks started coming off. However, in processing this, we were able to determine something else. The percentage that we were running at was 78%. The customer brought me the sample in 100%, I believe it was DCM. So we did have a little bit of DCM in there, more than what we actually had in the mobile phase. So we have to be careful that our sample solvent actually matches what we're putting in as a mobile phase. Because if not, what happened here, these were all equal injections, I should say. So the peaks actually pushed forward a little bit because the stronger solvent in the sample injections was actually pulling the first and second peaks mostly through the column a little bit quicker than they should have. So in this particular instance, the peak was pushed forward. The second peak was not quite pushed forward as much. And then as we got back here onto the last injection, we noticed that it's a perfectly resolved peak, well within the window of our initial parameters. So as I mentioned, make sure that you're not using improper solvents or higher concentrations of strong solvents to pull your sample through the column too quickly. We like to try and make sure that you're loading the sample in the same mobile phase composition that you're using for your run. Now on to the last couple sections of the talk today. So the next thing that I'm going to look into is some of the considerations that we need to look at for chiral and achiral purifications. We do have multiple different detector options, and I'm going to go through a little bit of each of the individual samples or the individual detection techniques. So most commonly used for both SFC and chiral purifications, reverse phase or normal phase, is UV or UV vis. With UV and UV vis, it'll help us to determine what would be the best optimal wavelength. So if you're not getting a very strong signal, obviously you would want to take the high absorbing area. But if you're running so much material that your peaks are starting to come together in chiral purification, sometimes you'll want to move off of that apex and go down a little bit further. So maybe instead of 220, maybe 230, and it'll allow you to see a little bit more of the separation between the two peaks instead of saturating your detector. The other thing we would look at is also if the wavelengths of the individual peaks themselves are actually identical, or if there may be a difference in the UV traces. If so, maybe you don't have a chiral separation. Maybe it's an impurity that's just co-eluting, or maybe it's just a simple other peak that is a similar response as your primary racemate. The next thing we can look at is the mass spec, which will allow you to give all kinds of better data than just the simple UV. You should be able to actually determine if, in fact, it is the same exact compound or if it is an impurity based on the actual mass response and the different fragmentation of each. The problems are it's a little bit more expensive and it is not as simple to maintain. The additional gas required for them can be costly. Some people will just use a house gas with a nitrogen purifier and a nitrogen generator. So it'll help save on some of the bottle cost of mass spec gas. Same thing with the LSD. You're also going to have an external gas, but the detector itself is less expensive, but it does give you a more accurate determination of the amount of material that's actually going through the detector because of the way it works. So we can actually see some compounds that don't show up at all on UV vis. Maybe it doesn't have a very strong ionization. So that'll allow us to see certain kinds of compounds that we can't see on the other two detection. So there's a use for each and every one of these individual detection techniques. There are also other ones out there like fluorescence conductivity. You can get some specific chiral detectors or even some refractive index detectors for different types of compounds, depending upon what you're looking for. So what do we do about optimizing the UV settings for recovery? Again, like I mentioned, this is a nice little picture that I grabbed from the instrument of our individual compounds. So it'll actually give you the full UV spectrum of your compound. So we can actually click on that and add that to your report after the run is over. And if you wanted to do that for both peaks, it will allow you to actually give you confirmation that those are in fact enantiomers for your reports after the runs are over. Typically, we do have the diode array, as you can see here, where we actually have a full spectrum. We have two different settings. We have a UV and a UV vis. So if you want to go up into the higher wavelengths for the visible range, we can also do that as well. This allows us also to see if there's something going on with our mobile phase. So if you have something in your mobile phase that's giving you a lot of suppression of UV in these areas here, it's also going to give you suppression of UV in your actual peaks here. So we may want to choose a wavelength that might not be as interfered with by your mobile phase. And as I mentioned before, quite frequently chiral separations will actually take a wavelength that's a little bit off of your UV max, just so that we don't saturate the detector and make it look like we have one big peak that just goes up here and then comes back down. If you go a little bit off wavelength, you'll start to see a little bit of a dip between the two compounds as they're coming off in the UV signal. On this final slide here, what we're showing is the 4 different columns running at 4 different flow rates. But on each of these individual chromatograms, you'll see that the peaks of interest, and this being on a 42.5 millimeter, 30 millimeter column, the UV, ELSD, and MS traces are all well aligned. We do that by utilizing a valve inside of the ACCQPrep that actually changes the flow path to allow us to compensate for the differences between the UV detector volume, delay volumes, and the external detectors, i.e. the ELSD and the mass spec delay volumes, so that we can basically match those up and allow them to have identical timing within the software. So we can take and use any one of the traces to do our fraction collection without losing any of our material by the peaks being out of alignment. It's uniform with all of our systems, so you don't have to worry about one instrument being different than another instrument. They should all have the same exact elution delays. So we can actually use the software to compensate for that when we do our collections. So the next slide, that brings us to our question section of our talk today. So one of the first questions that we've gathered during the webinar is there any way to pre-purify your sample, or if you can, what's the best way to purify your sample so that you don't have to worry about impurities? And we do have instruments that do that. You could also do a simple gradient to get rid of all the early and late impurities. So you just have either your racemate or your single pair of components that you want to try and separate. You could also use, we have a flash system, which is our next gen, which is a large scale purification that gives you a pretty good purification of just your bulk material, your main component. And then you can go ahead and purify using the stacked injections, which we've shown here. What are some other uses for this technique is another question that came through. So you could always use this for oligonucleotides, proteins, pretty much any purification where you have a very tight separation, but you can run an isocratic run to get a relatively small window of where your impurity may collude with your compound. As long as you can get some minimal resolution between the compounds, you can actually isolate into sections so that you can actually get a pure, impure, and then another pure fraction out of it. Oh, here's a good one. Does stacking save time and or solvent? It will actually save both, because what you'll wind up doing is you're utilizing the column to its fullest extent. So you always have compound on the column, and you don't have to worry about wasting that whole startup time. The length of your run, as I mentioned during my talk, will actually give you a lot better, how shall I say, efficiency if you have a very long run to start with. So if you have a very long isocratic run where there's a lot of startup and you have a very minimal amount of time on your cycle time, that's where your efficiency becomes really, really good. So that's what we're trying to look for. There are some instances where stacking just doesn't make sense, where you can go ahead and just make one single injection and have a fully pure sample by the time you're done. So when you get into those questions, by all means, reach out to us and we can certainly help you with those questions as well as you start to scale up. Another question that came in is what size of columns could you use? And it's a great question. We can pretty much use stacking on any size column that you like. Typically, the longer the column will help you for chiral separations, just so you get a little bit better resolution. And now that's on the normal phase on the ACCQPrep HP150. With the SFC instrument, we've been seeing a lot of people go with smaller columns and loading less material and just getting a really good separation and stacking a lot of very, very quick injections. If you're doing normal phase and you want to optimize the length of that startup time, another thing you could do is actually, because this is another question that's later on, is can you use two columns back to back? And that is definitely a good idea. Or use a 50 centimeter column. I know we used to use a bunch of 5 by 50 centimeter HPLC columns. Traditionally, most people on a walk-up instrument are usually using 15 centimeter long to 25 centimeter long columns for standard purifications. But the longer your column, the more efficient stacking becomes, because you have that startup length and you can get rid of that long startup length, and you have a lot more column to keep your compound on. So, but in those instances, we definitely want to make sure that you have a very reproducible, unmoving peak through your column. So you don't have to worry about maybe having to collect before or after your peak. It'll help you to maintain a stasis throughout the entire process. What are the limitations on the new version for the HPLC HP150? The limitations are basically going to be 150 mils a minute on the upper end for right now. That's pretty much going to be your limitation. One of the things that's really nice about our instrumentation is for fraction collection, you don't have to worry about the limitation of vessels or tubes, because if you do scale up to a large size, we can do 250 mil French square bottles. If you want to go even further, we have collection funnels that actually collect into bottles off of the instrument. So you can basically have unlimited collection into maybe 4-liter bottles or even larger. With the SFC, that's already built into it. So the SFC instrument actually has the solvent or the fractionation valve on the side of the instrument. So you can always collect into individual vessels that will have unlimited volume as well. So I think that, yep, that does it for the questions. And I think that's it. So I'm going to go ahead, and the next page, or the next slide, I should say, we're going to go ahead the company information. So as you can see, we have our Facebook, Twitter/X links, as well as our LinkedIn and YouTube pages. So if you want to, I'll leave them here for a second so you can see those. And for the last page, I'm going for joining us today for this webinar. As you can see, I have my QR code for my LinkedIn address there on the right-hand side. So if you want to go ahead and scan that, it'll take you right to my LinkedIn page, so you can link in with me there and ask me any questions you have, as well as my email is there in the middle. And as always, you can always reach out to our marketing team at Teledyne as well on the page that I just showed you. Thank you so much for joining us again, and have a great day.